We often think of black holes as destroyers. They suck everything within their reach into them and give nothing back. They are the end, the final destruction of the universe. And yet, what if I said to you that they might actually prove to be our salvation? Black holes might provide the answer to traveling faster than the speed of light and solving the energy crisis in ways we couldn't have even imagined until recently. And, as by now I have come to expect, they do so by messing with the fabric of reality itself and by completely countering my expectations of physics. Perhaps we have been thinking about black holes all wrong. I'm Alex McColgan and you're watching Astrum. Join me again for the 5th video in my series about black holes, where once again my mind has been blown by the incredible potential and implications of these very real objects in our universe. I've talked before about the formation of black holes in this series, including aspects about their event horizons, how they are created, and how they might possibly end. But to understand how a black hole ignores the usual limitations on faster than light travel and does so in a way that you can benefit from it without having to go inside a black hole's event horizon, and how it produces near limitless energy at the same time, then we are going to have to understand more about the features of black holes than we've covered so far. So, a quick recap. What is a black hole? In its simplest form, a black hole is an object in space that is so massive and so dense that the gravity it creates is too powerful for anything to escape it. We are familiar with the iconic black spherical zone that surrounds a black hole. This is the black hole's event horizon. This sphere is the demarcation point between escapable gravity and inescapable gravity. Because the gravitational pull increases the closer you get to a black hole, once you go beyond the event horizon, nothing, not even light, can travel fast enough to get away again. Beyond that though, it's actually quite difficult to say much about a black hole's features at all. Precisely because of the event horizon, we cannot see what the inside of a black hole looks like. In fact, there are only 3 things we can say about black holes with any degree of certainty. They have mass, they have charge, and they have angular momentum. You might wonder how we know these things about black holes, given that no light can leave them to tell us about them. The key to these 3 characteristics is that all 3 of them represent aspects of the black hole that can be felt outside the black hole's event horizon. Charge, for instance, works the same way around a black hole as it does around any other charged object. That is to say, if a black hole is charged, then it will attract objects that have different charge to it and repel objects that share its charge. Think of it like a giant magnet, pushing and pulling on the universe around it. Scientists can track objects that approach a black hole, and by seeing how quickly certain objects known to have a charge move towards it, scientists can predict the charge of the black hole itself. Interplaying with this is mass. The mass of a black hole can also be felt outside the sphere of the event horizon. In fact, it is the main creator of the event horizon in the first place. This is because mass creates gravity and does so in a linear fashion in accordance with the same principles you might find in Gauss's law, a theorem about electromagnetism, albeit with a gravitational analog. So, it's possible too to calculate the mass of an object by seeing how far away objects are before they start to accelerate towards it, and how quickly they accelerate. Although obviously, you need to factor in charge at the same time or your results might get skewed. Finally, angular momentum, or spin. It is possible to detect the spin of a large mass object, and we are going to dive into the how in just a bit. For now, let's just accept it as a given and recognize that black holes are certainly very high mass objects. Before we get into the different types of black holes, I want to talk to you about a new type of headphone. The sponsor of today's video, Raquel, have developed ingenious bone conduction headphones for when you're active that don't need to be inserted into your ear. They sit outside it, sending waves of sound vibrating through your very bones, giving you a crisp way to hear your music without blocking your ears from the rest of the world. Now, when on a run, you can easily hear music and be aware of approaching traffic,
or you can talk to someone without having to plug out of the music. They are lightweight and easy to wear, so are perfect for me when I'm tidying up but want a podcast to listen to, which happens a lot. Best of all, they are premium feel without a premium price tag. Right now there's even a 15% discount for Astrum viewers when using the link buyraycon.com/Astrum Extra BC in the description below. Go check them out.
Now, let's get back to black holes. There are varying sizes of black holes in existence. The smallest, known as micro black holes, have a mass that's comparable to that of our moon, or 7.35 times 10 to the power 22 kilograms. They fit all this into a space that's just 0.2 millimeters in diameter, which is incredible. It really gives you a sense of how dense a black hole can be, something thinner in size than a human hair, packing the mass of the moon. And that's just the smallest ones. Stellar black holes have a mass equal to 10 times our Sun, and have a diameter equal to 60 kilometers. Intermediate black holes are the mass of 1,000 suns, and fit all of that into a diameter of 2,000 kilometers, which is still much smaller than the Earth. It is the largest black holes that really dwarf us, with masses between 100,000 to 10 billion times the mass of the Sun, and sizes ranging from 0.001 to 400 astronomical units, an astronomical unit being the distance from the Earth to the Sun. But other than those three features, there are in theory no other differences between them. If you put two black holes in the same room and made sure they had the same mass, charge and spin, it would be impossible to tell them apart. However, these three features are enough to have some interesting effects on the area of space outside a black hole. Traveling inside a black hole is impossible. Space and time break down past the event horizon, but we think we know a few things that must exist inside one. Beating in the heart of a black hole, there is thought to lie the singularity. In truth, this actually is the black hole. When we were discussing diameters earlier, that is just the diameter of the event horizon. Again, we are not certain what a black hole actually looks like because light can never escape it. In a space that is infinitely small, there is a point where all the mass of the black hole is packed, so that it is infinitely dense. For the simplest models of black holes, the ones that do not spin, this is a single point. In a rotating black hole, this is more like a little spinning ring, otherwise it would be difficult to define spin for a point that has no volume. Our current physics get very strange around such a black hole. If ideal paths are travelled around this point, it becomes mathematically possible to do some very strange things, like meet up with your own past. This has some disturbing implications for causality and gets into time travel paradoxes like the grandfather paradox. So that probably only shows for certain that our ideas about singularities are not quite right yet. Because the singularity is so small, it'll take the successful merging of quantum theory and general relativity theory to properly explain what is going on inside a black hole, and we have not yet managed to do this. It may one day turn out that singularities do not exist in the hearts of black holes at all, but this is the extent of our knowledge so far. Well, whatever it is that lies inside a black hole, it powers our faster-than-light engine, because like most objects in the universe, it spins. And oh, does it spin! As we travel out from the center of the black hole, we pass through the event horizon with little fanfare. The event horizon actually cannot be detected locally, although a person outside the black hole might watch you slow down to a complete stop as you travel through it. From your perspective, it actually might seem like time is flowing normally. Normally, that is, until the universe outside the black hole runs its course in an instant, because time outside the black hole is traveling so fast compared to you. This is the essence of relativity, and we talk about it in another of my videos, which you can look at here. In fact, the only evidence you might have that you've passed the event horizon at all is because of something that exists just outside it, the photon sphere. In a zone just outside the event horizon, there exists a point in space where if a photon enters it at just the right angle, it will enter a perfect orbit around the black hole in much the same way the moon perfectly orbits the Earth. This infinitesimally thin zone is known as the photon sphere, and given the number of photons that have flown past black holes in all the millions of years they have existed, it is probably filled with photons. It is quite possible that you would be instantly fried as you pass through this point. However, it is just outside here that we find the zone that interests us, the ergosphere. This is the zone around a black hole where we can most easily detect its spin, and this is because, in this zone, it is impossible for us not to move. You see, mass affects space. We see this in the curving effect of gravity on the travel of objects through that region of space. However, it might be more accurate to say that mass drags on the space around it. As it moves through space, it brings a little bit of that space along with it for the ride. And when an object as massive as a black hole spins, there is an effect known as frame dragging. To put it simply, reality around the black hole begins to spin in a whirlpool that cannot be fought against. Much like a real whirlpool, anything caught within the ergosphere is spun around the black hole, because the frame of reference it sits in is being pulled. Sort of like how a person moves because they are standing on a moving walkway. The greater the spin of the massive object, the faster this happens, and in the ergosphere, this can occur at a speed so fast that by the event horizon, space is moving faster than the speed of light. You would need to travel faster than the speed of light in the opposite direction just to stay at a relative standstill from the point of view of the outside observer, which of course you cannot do. But isn't this against the laws of physics? Doesn't Einstein say that nothing can travel faster than the speed of light? The answer to that is yes. But black holes have found an interesting loophole. You see, this rule only applies locally. Right where you are, in your frame of reference, nothing can go faster than the speed of light. But thanks to relativity, it is possible for frames of reference to move away from each other so fast that objects in them appear to be breaking this light barrier from your point of view. But if you move next to them and enter their frame of reference, they would seem to slow down and would start obeying the laws of physics again. It's a really weird effect, but frame dragging is an actual thing. It is by measuring frame dragging that scientists can learn the spin of a black hole. However, according to a man called Roger Penrose, there may even be a way of exploiting it. If you were to send a rocket into this section of the ergosphere, the rocket would speed up due to being caught in the whirlpool of reality. Once it had gained enough speed, it could then fire a propellant in such a direction that it pushed itself out of the whirlpool again, but now traveling at a much faster speed. This method, named the Penrose process, could hypothetically net you energy equal to about 20% of the mass of your rocket. Now, that might not sound like much, but remember, according to Einstein's E equals mc squared, your 20% mass would produce energy equal to itself times by 299,792,458 squared. That's a lot of energy. So to harness this colossal kinetic energy, all you would need to do is travel to the nearest black hole, which is roughly 3,000 light years from us, and enter its ergosphere with a rocket capable of surviving the intense gravitational forces there. Ideally, you would need to find one that was not surrounded by an accretion disk, because those get up to temperatures of millions of degrees, as they are swung around at near light speeds and melt from solids down to gas and plasma. But you get the idea. Easy. Okay, maybe this is a little impractical for us, but the implications for faster than light travel that black holes demonstrate through frame dragging might just offer us the key to one day beat the light barrier for real. Not by going faster than light ourselves, but by somehow convincing the frame of reference we are in to travel at those faster speeds, just like they do around a black hole. Of course, if this requires the energy of a black hole to accomplish, we might be out of luck for now, but it's an incredible glimpse into what is possible, and scientists are already looking into the power of frame dragging for future travel. But maybe that's a topic for another video. Either way, this all just highlights once again how our universe really is very different from what we might have ever imagined.
If you're a long-time viewer of Astrum, you'll already know that Betelgeuse is no ordinary star. Betelgeuse is a red supergiant in the Orion constellation that's just 650 light-years away from the solar system, making it the second largest and 10th brightest star in the sky, not counting the Sun. A few years ago, Betelgeuse made headlines when the bright supergiant appeared to be getting dimmer, indicating that it might be about to explode in a supernova. But that wasn't the only surprise that Betelgeuse had in store for astronomers. Measurements from the ALMA array of telescopes have detected that Betelgeuse is rotating at a mind-bending rate of, well, just about once every 20 years. Okay, that might sound a little underwhelming, but for a star the size of Betelgeuse, this means that the surface is spinning at a speed of 18,000 kilometers per hour, or about 5 kilometers per second. That's 10 times faster than our own velocity on the surface of Earth, and for a massive supergiant star, it all but breaks the laws of physics. I'm Alex McColgan, and you're watching Astrum. Join me today as we dig into the unusual surface of Betelgeuse and the secrets behind its seemingly impossible rotational speed. Let's start with the basics. There are a couple of different ways to measure the rotation of objects in the night sky. If the object is big enough, like the Sun, the Moon, or even a planet in our solar system, it's easy enough to point a telescope at it and watch its features move in real time. For reference, the angular diameter of the Moon is about half a degree, and you can probably make out its features with your own eyes. Jupiter's angular diameter comes in at 1/100th of a degree, but its features are still clearly visible through a telescope. So, what about Betelgeuse? The supergiant star just 650 light-years away. For all its size, Betelgeuse is still far enough away from Earth that its angular diameter is 1,000 times smaller than Jupiter's, making it look like a total blur to even our most powerful telescopes. Luckily, there's another way to tell whether a star like Betelgeuse is rotating. It's less direct than just, well, looking at it, but it's an ingenious technique that relies on a simple effect you might have already heard of: Doppler shift. The same effect is also responsible for the change in pitch from a siren as an ambulance passes by. When the ambulance is moving towards you, the siren sounds higher pitched because the sound waves hit you at a higher frequency than if the ambulance were standing still. But as soon as the ambulance starts moving away from you, the effect reverses. Sound waves hit you at the lower frequency, and the siren sounds lower pitched. What you probably wouldn't notice is that the Doppler shift affects light waves bouncing off the ambulance, just like it affects the sound waves coming from its siren. The higher frequency light as the ambulance approaches makes it look ever so slightly bluer. And as soon as it starts moving away from you, the effect flips and it looks ever so slightly redder. The only reason this visual effect isn't obvious is because the speed of light is 1,000,000 times faster than the speed of sound, so it would take a much faster ambulance for us to actually notice the optical Doppler shift. We might not have ambulances here on Earth flying by at 5 kilometers per second, but those kind of speeds are fair game out in space. Which brings us back to Betelgeuse. When a star is rotating, half of its surface will be moving towards us, while at the same time, the other half will be moving away. This creates a gradient of colors emitted by the star that we can observe with our telescopes, even if the star is too blurry for us to make out any of its distinct features. By seeing which side is bluer and which side is redder, we can infer the direction of rotation, and by measuring how different the bluer frequencies are from the redder ones, we can calculate the star's rotational velocity. This was the technique used by astronomers to analyze the data collected by ALMA and conclude that the surface of Betelgeuse was spinning at 5 kilometers per second. That's all well and good, except the known physics of spinning stars predicts that 5 kilometers per second is far too large a velocity for a red supergiant like Betelgeuse. Take our Sun as an example. Its rotational speed is in the same ballpark, around 2 kilometers per second, but is also 1,000 times smaller and about 10 times lighter than Betelgeuse. If our Sun expanded to the size of Betelgeuse, which would envelop the entire inner solar system and nearly reach Jupiter's orbit in the process, then its velocity would drop to just 2 meters per second in order to conserve angular momentum. In the same way that a spinning ice skater slows down when she spreads out her arms. And if the Sun grew 10 times heavier to match the mass of Betelgeuse, its velocity would drop to 0.2 meters per second. So, the larger and heavier a star is, the slower we expect it to spin. And yet, Betelgeuse appears to defy all of those expectations. What's going on here? One possible explanation is that even though Betelgeuse didn't start out with this much angular momentum, it gained it through a process known as stellar cannibalism. As you might expect, stellar cannibalism is just what we call it when one star eats another star, usually its companion in a binary orbit. In more scientific terms, the star's gravity pulls away its companion's gas, layer by layer, until only the inner core remains. That gas carries most of the companion star's angular momentum, so the first star ends up not only growing larger, but also spinning faster than nature would normally allow. But is this really the story of how Betelgeuse got its spin, or is there something even more mysterious happening under the surface? A team of researchers collaborating across Europe and China have recently suggested that Betelgeuse's apparently ludicrous rotation speed might just be a giant optical illusion. To see how that's possible, let's think back to what the team at ALMA really measured with their state-of-the-art array of telescopes. Though their pictures of Betelgeuse were blurry, they were still able to make out that one half of the star emits slightly redder frequencies of light than normal, while the other half emits slightly bluer frequencies. The obvious explanation for this 50-50 split is that the star is rotating, with one half moving towards us and the other half moving away from us at the same time. The green arrow in the image of Betelgeuse is meant to represent the axis of this rotation. But what if that's not the only explanation for the color gradient detected by ALMA? Simulations of Betelgeuse have revealed that its surface is a chaotic, turbulent place, constantly bubbling under its own heat like water bubbling in an oven. Each of these bubbles is enormous and propagates outwards at deadly velocities. A single bubble can be 100 million kilometers across, covering a large fraction of the surface of Betelgeuse. And if one of these bubbles were headed your way, even today's most powerful spacecraft wouldn't save you from its lightning fast speed of up to 30 kilometers per second. Your only hope would be for the bubble to pop and crash violently back down onto the surface before it ever reaches you. As gas bubbles all over Betelgeuse rise and fall, its surface becomes a mosaic of regions that are either moving towards us or away from us as observers on Earth. In turn, the Doppler shift causes light emitted from these regions to be either blue shifted or red shifted. In a recent paper that rose to challenge all previous explanations of Betelgeuse's rotation, the international team of researchers proposed that Betelgeuse might not be rotating fast at all. Instead, the ALMA observations might be detecting a range of light frequencies coming from Betelgeuse due to the turbulence on its surface. Thus, astronomers may have been misinterpreting those shifts in frequency as rotational effect. But if you've been paying close attention to the physics, you might have noticed that there's still a loose end with this alternative explanation. A rotating star should produce a smooth gradient of light frequencies, ranging from bluer than expected light on one edge to redder than expected light on the other. Meanwhile, A turbulent star should produce a random patchwork of colours, with bluer patches where bubbles happen to be rising and redder patches where bubbles happen to be falling back down. How could the astronomers at ALMA possibly have mistaken one for the other? If astronomers observed a smooth gradient of colours coming from Betelgeuse, shouldn't the patchwork explanation already be ruled out? In an ideal world, that would be true. Gradients would correspond to rotation, and patches would correspond to bubbles. But remember that Betelgeuse is so far away that the image captured by ALMA is far from ideal, and it's more of a blur than an HD photograph. When simulations of the surface of Betelgeuse are made to account for the limited resolution of observations, they predict that the bubbly patches of redshift and blueshift will be easily mistaken for a rotational gradient about 90% of the time. This means that even if the astronomers at ALMA did nothing wrong in their analysis, they may have been fooled by Betelgeuse's boiling surface into thinking it's spinning way faster than it actually is. This also means that astronomers are now chasing after one key objective: higher resolution studies of Betelgeuse that could more accurately tell the two scenarios apart. The good news is that better images of Betelgeuse already exist, taken by the same telescope but with longer exposure times. The bad news, for those of us who are more impatient, is that it will likely take a couple of years for them to be properly analysed. Those answers are coming though. For now, I'm curious to know where you would place your bets. Is Betelgeuse really spinning at 5 kilometers per second after having eaten its companion star? Or will the new claim that this rotation speed is nothing more than an optical illusion be vindicated? Let me know your thoughts in the comments below. In 2022, astronomers using the Murchison Wide Field Array discovered a strange new radio signal that was arriving every 22 minutes. The astronomers were no strangers to such repeating signals. They typically come from pulsars, neutron stars which send intense pulses of light across the universe as they rotate on their axis. But as they began to look deeper into records of past observations, they realized this signal had been arriving at Earth since at least 1988, with remarkable stability, far more stable than is expected for a pulsar rotating every 22 minutes. If it was a neutron star, it was unlike any they had seen before. So, where was this signal coming from? I'm Alex McColgan, and you're watching Astrum. Join me today as we grapple with the mystery that lies behind this signal, which will challenge our understanding of some of the most awe-inspiring objects in our cosmos. The location of the source, named GPM J1839-10, is roughly 18,000 light-years away. Its signal arrives as pulses that can last any amount of time between 30 seconds and 5 minutes. These pulses can appear at any time in a window of just over 6.5 minutes, which is centered on 22 minutes after the previous pulse. To us, this may seem like a great deal of variation. 30 seconds and 5 minutes are very different durations, and the pulse arrival varying by over 6 minutes doesn't paint a picture of a very stable source. But neutron star dynamics can be very complicated, and if the source is indeed a neutron star, then many factors can affect the duration and arrival times of the pulses that we receive. Nevertheless, the astronomers were able to spot this signal hiding in data from the last 35 years and used this expanded dataset to average out the fluctuations. They calculated that the source was rotating once every 21 minutes and 58 seconds, as well as how much it had slowed down. But to their surprise, they calculated that this rotation period remained unchanged over the past 35 years, even though it is expected that the source will slow down as it radiates energy into space. We can only say for sure that if the source has slowed down, its rotation period would not have increased by more than 0.28 milliseconds over the 35-year period, because otherwise we would have been able to detect this in our data. This is an absolutely minuscule amount, and it shows that whatever the object is is spinning with remarkable stability. This usually isn't odd for a pulsar. These are the timekeepers of the universe, the clocks of the cosmos, mechanistically ticking away with such certainty that we can use them to measure time across vast stretches of the universe. However, this level of stability is odd for a pulsar that is rotating so slowly. To understand what makes it odd, we need to recap how pulsars work and what makes them slow down over time. Pulsars are neutron stars, the leftover cores of dead supergiant stars which, barring black holes, are the densest objects in the universe. Planets like our own are made up of atoms, which consist of over 99.999% empty space due to the vast separation between the electrons and the incredibly dense nucleus they are whizzing around. But imagine an entire star made purely out of the neutrons that are found in the nucleus. No electrons, no protons, no empty space. Merely a teaspoon of it would have as much mass as 11 times that of the entire human population, all 8 billion people. A typical neutron star is around 35% more massive than our Sun, and squeezed into a sphere that has the diameter about as long as the island of Manhattan. To call it dense would be an understatement. For reasons still unknown to astrophysicists, the extreme environment gives rise to an incredibly strong magnetic field. What does this have to do with the signals we receive from pulsars? Where do the light waves come from? To answer this question, we need to understand a complicated process that gives rise to the signal, an exponentially growing shower of light and matter, all spawning from a single electron. Near the magnetic poles of a neutron star, an electron can be accelerated by the magnetic field and emit a so-called curvature photon, tangential to the magnetic field line. This marks, if you like, the start of a pulse. The curvature photon moves in a straight line until the angle between its momentum and the magnetic field line becomes too great. Once this angle reaches a threshold, the light dissipates and imbues its energy into the quantum field of electrons. An electron is created alongside its antiparticle, the positron. The electron-positron pair has some momentum perpendicular to the magnetic field lines, which they spontaneously dispose of in the form of synchrotron photons. These two synchrotron photons can each then produce another electron-positron pair after they reach the threshold angle between their momentum and the magnetic field lines. This process repeats again and again, exponentially increasing the amount of photons and electron-positron pairs created until the synchrotron photons no longer have enough energy to create electron-positron pairs, putting an end to the cascade. These photons then beam out into space, while the original electron continues its journey, generating more curvature photons and more cascades as it moves along the magnetic field lines. This pair production cascade is why the light of a pulsar is so intense that we can detect a signal from this tiny stellar remnant thousands of light years away. But why do we see this light as pulses rather than a continuously glowing beacon of light shining at us? This is because the magnetic poles of a neutron star are rarely ever aligned with its axis of rotation. Just like on Earth, the magnetic North Pole that our compasses point to isn't the actual geographic North Pole the Earth rotates around. So, the pulsars are like great lighthouses, sweeping their beams of light around the cosmos as they spin. And for an observer far away, like us on planet Earth, we see the beams sweep past us again and again as the pulsar completes its rotation on its axis. These are the pulses of light that our telescopes can detect. However, this is light with very long wavelengths in the radio part of the spectrum, meaning only a radio telescope can detect it. The light that the cascade produced is of the same wavelength, with the peaks and troughs of the light waves fluctuating in unison. The light waves are also polarized, which means they are all aligned along the same axis.
This is a hallmark of neutron stars, and this is precisely what we observe in the 22-minute signal. The signal also has fluctuations that last between 0.2 to 4 seconds, where the axis of the light's polarization suddenly changes by 90 degrees, perpendicular to the original axis and then back again. This effect is yet another signature of the cascades at the poles of the pulsars. So much of our data points to a pulsar being the signal that you'd think this was an open and shut case. But one variable that we've mentioned earlier throws this entire theory into doubt: the slow rotation rate of the neutron star. Or rather, the combination of the slow rotation rate and the high stability of the rotation rate of the source. You see, as pulsars lose energy by shining their powerful beams into the cosmos, conservation of energy will ensure that the pulsar slows down. Eventually, the pulsar will slow down so much that it can no longer power the pair production cascades, and the light emission starts to shut off. The pulsar has entered the so-called Death Valley. This graph plots neutron stars based on their rotation period on the x-axis and the rate of change of their rotation period on the y-axis. Death Valley is shown in this grey band running through the middle, and any pulsar that has properties below this line should not be shining as the bright lighthouses they usually are. We see that our signal is below even the lowest line marking the Death Valley, meaning that if it were a pulsar, it should be well and truly switched off, and yet we are detecting it. Look at the cluster of other known neutron stars on this graph. They usually spin between 10 times a second to once every second. In comparison, our signal has a spin rate of once every 1,318 seconds, over 1,000 times slower than the typical pulsar. This would be fine if it was also slowing down quickly, which equates to moving this data point upwards on this graph above the Death Valley. Such rapid energy loss would power the pair production cascade necessary to light the beacon of the neutron star. Yet, the neutron star is mind-bogglingly stable, and it makes no sense that we can detect it. The astronomers who found the signal considered an alternative mechanism that might explain how a neutron star with such properties might have produced this light. Maybe the neutron star is a magnetar, a neutron star that has an unusually strong magnetic field, greater than 10,000 times the strength of the weakest neutron star magnetic fields. Magnetars are known to undergo starquakes, cataclysmic events that release the tension in the upper crust of a neutron star. These stresses are produced by the strong magnetic fields of the magnetar, as well as the slowing down of the magnetar rotation. A fast-spinning magnetar will bulge in the middle due to the centrifugal force distorting the star from a perfect sphere. As the magnetar slows down, the outer layers need to readjust to a new equilibrium and lose some of the bulge they have. The crust snaps into a new position, causing magnetic fields to temporarily realign and powering the release of the energy as light that we can detect on Earth. The most powerful starquake detected, that of SGR 1806-20 in 2004, released so much energy that if it had taken place as far away as 10 light years from Earth, it would have caused a mass extinction event. If something is able to light the beacon of a dead pulsar, it would be this. So, could GPM J1839-10 be a magnetar that has undergone a starquake? Have we resolved the mystery of the 22-minute signal? It seems not. We expect these starquakes to also emit light in the X-ray part of the spectrum, yet no X-rays can be detected from the position of the source roughly 18,000 light years away. It also wouldn't make sense for a magnetar outburst to be going on for 3 decades. The starquake is a temporary phenomenon, and the energy dissipates within a few years at most. It is simply incomprehensible that this signal would have existed for 35 years if it was indeed a magnetar. Once again, the unique properties of our signal exclude it from being a neutron star. even an unusually powerful one that has undergone a special event such as a starquake. But what else could the source of this mysterious signal possibly be? The astronomers who discovered the signal proposed a few alternatives for the identity of the source. One possibility is a highly magnetic white dwarf. A white dwarf is another type of remnant left from the recent death of a star, but one that didn't have enough mass to collapse the empty space in the atoms to become a neutron star. A remnant that has an unusually strong magnetic field could produce radio emissions, and as it is not a neutron star, it could get away with being as slow and stably rotating as the source of our object while doing so. The issue is, this would require an exceptionally strong magnetic field, greater than any we have spotted on a white dwarf. AR-SCO is the only known radio pulsar that is actually a white dwarf, and its radio emissions are 1,000 times less luminous than the source of our 22-minute signal. So, if a white dwarf is unlikely, what are our other options? Astronomers have observed low-frequency radio waves coming from the interactions between stars and exoplanets, as well as a binary of two brown dwarfs rotating around each other, but this emission is typically weaker, around 100 million times weaker than the source of our signal. In the end, it seems like none of our theories can explain the 22-minute signal. While the unresolved question about the source of the signal may feel frustrating, this is precisely the kind of mystery that astrophysicists look for. When scientists find new data that challenges our long-held theories, they can usher in revolutions in our understanding of the universe around us. Here, our already shaky understanding of neutron stars is being challenged. The astronomers are confident that the ease with which they identified this signal means similar sources lie out there in the galactic plane, waiting to be identified. Just like GPM J1839-10, the other signals might already be lurking in the data we have collected. Identifying more of these signals will shed light on the process powering emission beyond the neutron star Death Valley. Whatever lies behind the 22-minute signal, we are sure to learn of an entirely new phenomenon that we have never seen before. Isn't that exciting? What do you think could be the source of the 22-minute signal? Let me know in the comments below. 800 light years away, there's an unseen antimatter factory churning out high-energy positrons. Tiny particles of antimatter that are streaming through the cosmos and colliding with our planet. For much of history, we didn't know this strange source existed. Most of the positrons bombarding us went completely undetected, instead getting absorbed in our planet's atmosphere. It wasn't until we started looking from beyond the bounds of our planet that we noticed them. In 2011, NASA's Alpha Magnetic Spectrometer, a state-of-the-art particle detector some 200 miles up aboard the International Space Station, was switched on. What did it find? You guessed it, positrons. The presence of these subatomic particles was to be expected, but not in the numbers they were finding. Such was the sheer volume of positrons being detected that the usual sources like natural radioactive decay and cosmic rays no longer offered a sufficient explanation. So, where were they coming from? We've only recently been able to trace the culprit of this cosmic antimatter shower, and it all comes down to another high-energy discovery. A strange gamma-ray haze named Geminga, first identified in the 1970s. What is this mysterious source of gamma radiation? And what does it have to do with the unusual abundance of high-energy positrons hitting our planet? I'm Alex McColgan, and you're watching Astrum. Join me today as we tune into the enigmatic frequency of Geminga, whose gamma radiation has lit up the world of astrophysics for decades. Up in our night sky, nestled in the Gemini constellation in the northern celestial hemisphere, there is something peculiar going on. In 1972, NASA's Small Astronomy Satellite 2, or SAS-2,
identified an unknown source of gamma radiation. But with the technology available at the time, the best it could do was trace its origin to this wider region of our Milky Way. So, the radiation's ultimate source remained hidden among the stars for decades. Nevertheless, it was given a name, Geminga, as coined in 1976 by Italian physicist Giovanni Bignami, who would dedicate his career to studying it. It's a play on words, a combination of Gemini, the region where it's located, and gamma, the type of radiation it emits. Geminga is also a pun in Bignami's Milanese dialect, meaning "it's not there," a fitting name for a gamma-ray haze with unknown origin. It wasn't until 1983 when Bignami and his team finally had their big break. They managed to identify a weak X-ray signal from Geminga using the Einstein X-ray satellite. This meant, although its exact position remained unknown, they could narrow down their search area and were getting closer to uncovering Geminga's hiding place. But it didn't answer the big question, what is it? As astronomers could still only offer vague guesses about the true nature of the source. That was until 1991, when they had another lucky break. 2 separate missions identified radiation coming from Geminga, and they weren't constant signals, but pulses. The first of these discoveries was made with a German-built X-ray telescope known as ROSAT, short for Röntgen-Satellit, named after the German word for X-rays. ROSAT was the first to identify pulses in the X-ray signal coming from Geminga, and soon after, they were also confirmed in the gamma wavelengths by the Energetic Gamma Ray Experiment Telescope, or EGRET, a telescope aboard NASA's Compton Gamma Ray Observatory satellite. Not only did these complementary observations demonstrate that the X-rays and the gamma rays were both coming from Geminga, but for the first time they revealed what Geminga was. With a period of 0.237 seconds, flashing as it spins around its axis a little more than 4 Hz, or 4 times per second, Geminga behaved like a pulsar. A pulsar is a type of neutron star that spins rapidly, emitting beams of radiation that sweep across space like a cosmic lighthouse. From across the galaxy, most pulsars appear to flash in radio waves, anywhere from a few times a minute to as fast as 700 times per second. And at this point in the early 90s, they were incredibly rare. You see, before ROSAT and EGRET, only 2 other high-energy gamma-ray pulsars had ever been identified, the Crab and Vela pulsars. And Crab and Vela were different to Geminga in a couple of key ways. First, in addition to gamma rays, both of these pulsars also produced radio waves, and were therefore visible using radio telescopes. So if Geminga was a pulsar, then it would be the first discovery of one that was apparently radio silent, only emitting enough radiation to be seen in the gamma and X-ray wavelengths. And second, Crab and Vela were surrounded by their respective nebulae, remnants from when they were created from supernova explosions. But Geminga's nebula was conspicuous by its absence. So why is Geminga, this powerful source of gamma rays, so good at hiding from our radio telescopes? Where is its nebula? Or could it be a different type of object altogether? Well, the answer to the first question is, in part, because we hadn't been listening properly, due to the limitations of the available technology and due to our understanding of the radio emissions of such stellar remnants. You see, while radio pulsars can emit radio waves across a wide bandwidth from as low as 17 MHz to above 87 GHz, around half the radio spectrum, not all of these frequencies travel well through space. Even though we've known since the 1970s that radio pulsars often peak between 100 to 200 MHz, where they are intrinsically brightest,
Things like the interstellar medium, background sky temperature, and effects from the ionosphere mean that lower frequencies are dampened as they make their way across space, resulting in very weak signals that are much more difficult to detect. Because those radio signals are so weak, most radio telescopes hadn't been looking for them, instead confining themselves to searching for signals between 430 and 1600 MHz. This would have been fine had Geminga behaved as expected for one of its kind. Since it did not, it took until 1997 for scientists to realize what was happening. 3 independent observations from the Pushina Radio Astronomy Observatory were able to identify extremely weak pulses from Geminga using a sensitive transit antenna. The faint radio pulses came in around 100 MHz, which explains why previous radio searches for Geminga had come up silent. Turns out, Geminga wasn't truly hiding and had been sending us signals. We just weren't listening correctly. That same year, a team led by the late astronomer Janusz Gill theorized that another reason Geminga had appeared to be radio silent may be its magnetic field. Models showed that radio waves may be absorbed or refracted within the pulsar's magnetosphere, leaving only weak pulses around 100 MHz to be detectable. This would effectively leave it quiet at the higher radio bands than most telescopes used. Confirming Geminga was a pulsar, and specifically a gamma-ray pulsar, was a big deal. In fact, 99% of its output is in the gamma range, making it one of the brightest gamma-ray sources in our entire galaxy. It is, as it turns out, all that's left after a star, several times more massive than our Sun, exploded about 350,000 years ago. But its relative radio silence and its apparent lack of a nebula weren't the only unusual things about this pulsar. When Italian astrophysicists, including Bignami, Geminga's name-giver, compared a series of observations from the European Southern Observatory's 3.6 meter telescope and New Technology telescope with observations from the Canada-France-Hawaii telescope, they found that Geminga was moving. Not only that, it was traveling at an unusually high speed of around 0.2 arcseconds per year. As a reminder, an arcsecond is a very small unit of angular measurement, used when we need more precise measurements than a degree would allow. Within each arc degree, there are 60 arc minutes, and within each arc minute are 60 arc seconds. These arcseconds are a common unit used in astronomy to talk about the movement of objects across the sky from our perspective on Earth. If you were to draw a circle around the orbit of the Moon around the Earth, there would be 360 degrees around that circular path. So at any given time of day or night, assuming nothing is blocking your view of the horizon, you can see about 180 degrees of the sky, and from the horizon to the zenith, the top of the sky, is 90 degrees. If you hold out your little finger at arm's length and close one eye, the tip of your little finger covers about 1 degree of the sky, roughly. Next time you're outside on a clear night, try this, and see if your little finger can cover the moon. It should, because the moon takes up only about half of a degree, or about 31 arc minutes in the night sky. Geminga traveling 0.2 arc seconds across our sky each year may not sound like a lot, but from our perspective on Earth, the typical star only moves a few thousandths of an arc second per year. Yet, despite being 800 light years from us, Geminga will travel 30 arc minutes, the equivalent to the apparent diameter of the Moon across our sky in just over 10,000 years. In other words, this stellar corpse is racing through the galaxy at nearly 210 kilometers per second. Heading towards the border between the constellations Gemini and Lynx, and at its current rate of motion, Geminga will remain in Gemini for another 500,000 years, but it may need a new name after that. However, this mysterious pulsar gets stranger still. It is its vast speed that helps produce another feature that scientists were about to discover. As it hurtles through space, Geminga leaves behind two ghostly X-ray tails that streak 3 trillion kilometers across the sky. As I discussed earlier, despite the fact that this fast-moving pulsar is nearly radio silent, it certainly isn't quiet in the gamma ray and X-ray wavelengths. In 1999, ESA's X-ray Multi-Mirror Mission, or XMM Newton, was launched to peer deeper into this X-ray universe, and 4 years later, a team led by Patricia Caraveo uncovered these comet-like X-ray trails. Their shape and brightness are partly explained by the shockwave created by Geminga's motion through space and its rotation as a pulsar, but they are also revealing of another attribute: Geminga's colossal mass. Measuring only about 20 to 30 kilometers across, Geminga is extremely dense, containing about as much mass as 1.5 of our suns. To put that in perspective, if you had a teaspoon of neutron star material, it would weigh about 4 billion tons, as much as 10,000 Empire State Buildings. As this dense, high-mass object races forward through the low-density interstellar medium, just 0.06 to 0.15 atoms per cubic centimeter, it compresses the interstellar medium and its own embedded magnetic field by a factor of 4. Meanwhile, the incessant spinning of the neutron star creates an environment where electrons and their antimatter counterparts, called positrons, can be accelerated to extreme energies, powerful enough to emit high-energy gamma rays. While most of these electrons are seen in the gamma radiation that escapes from the pulsar, some get trapped and spiral within this enhanced magnetic field. In these images from a computer model, the tails can be seen streaking along the edges of Geminga's 3-dimensional shockwave, like the wake created by a boat going through water. Only this boat is more massive than our sun, and the wake is made up of extremely high-energy X-rays. But the final piece of the Geminga puzzle wasn't discovered until 2005. Its nebula. Taking the form of a shell of neutral hydrogen gas with a radius of 0.4 parsecs wide, it turned out to be what we call a pulsar wind nebula. This type of nebula is created from the wind plasma that emanates from a pulsar's magnetic poles. The plasma, made of charged particles that can be accelerated to near light speed, surrounds the pulsar, creating a nebula of high-energy particles that give off strong X-ray emissions. With the confirmation that Geminga did have a nebula, its identity as a pulsar could finally be confirmed. But Chandra went even further. In addition to imaging Geminga, Chandra also looked at a second pulsar called B0355+54, and by comparing the two, astronomers uncovered another possible explanation for the absence of radio pulses from Geminga. On the surface, these pulsars seem quite similar. They are both about 500,000 years old, and they spin about 4 to 5 times per second. However, as you know, Geminga is seen primarily in gamma ray pulses, with no bright radio emissions. By contrast, the other pulsar, which I'll refer to as Pulsar B, is not seen in gamma rays, and instead is one of the brightest known radio pulsars. How could these two pulsars be so similar, yet so vastly different in how we see them? The answer may be as simple as how each of these pulsars are oriented relative to our observation from Earth. Astronomers believe that these images of Geminga and Pulsar B have revealed their spin axes and uncovered a reason for why radio and gamma ray pulses may be present or absent on different pulsars. Like our own magnetic field around Earth, Both of these pulsars have magnetic poles close to their spin poles. These poles are where the beams of pulsing radio emissions come from. You could try to model this if you skewer a little foam ball right down the middle. The foam ball is a pulsar, and the radio beams coming from the poles are represented by the wooden skewer coming out both ends. If you spin the ball around the skewer like a spin axis, you create an equator around the middle. To illustrate the gamma ray source along the spin equator, called the torus, you could cut a hole in a paper plate and squeeze it over the foam ball. Now you've got yourself a disk of gamma rays beaming out from the equator in every direction. With Geminga, the edge of the paper plate is pointing towards us, meaning the gamma rays are heading to Earth. But for Pulsar B, its relative position to us is at a different angle, as if looking at the flat surface of the plate. The gamma rays are moving perpendicular to our line of sight, therefore missing Earth. Let's look again at the two Chandra images of Geminga on the left and Pulsar B on the right, along with artist illustrations of what astronomers believe the pulsar wind nebulas look like for each of these. In the image of Pulsar B, the long trailing blue tails represent the radio jets emanating from its poles, and the skewers coming out of both ends. Only instead of being straight like a wooden skewer, Pulsar B is moving so fast through space that these jets appear bent backwards, trailing behind as the pulsar moves through space. Now look at the image of Geminga. Here, the long twin tails on either side of the image are the radio jets, trailing behind as it, too, rushes through space. But this time, instead of pointing almost directly toward and away from our vantage point on Earth, these jets appear to be coming off to the sides, not aimed at Earth. So when astronomers look at Geminga, they see powerful gamma ray emissions from the spin equator, but the radio jets point to the sides and remain unseen. And when they look at Pulsar B, the opposite happens. The radio jets are pointed almost straight toward our planet, while the gamma ray source at the equator is missing Earth. Sometimes, the most simple explanation is the correct one. And that finally brings us back to the decades-long mystery of an unusual abundance of antimatter bombarding our planet. For more than a decade, a particle detector called the Alpha Magnetic Spectrometer, or AMS-2, has been attached to the International Space Station, collecting information on antimatter, dark matter, and cosmic ray sources. As a reminder, cosmic rays are energetic particles, fragments of atoms that travel through space at nearly the speed of light. These can be made by the sun, by supernova explosions, or other cosmic means. And in 2013, the first results of the AMS-2 experiment were announced. The detector had recorded more than 400,000 positrons, the largest sample of cosmic ray positron data ever collected, and increasing the world's total cosmic ray positron data by 100-fold. For years, many astronomers and physicists hoped that this excess antimatter may be the byproduct of a dark matter annihilation, offering possible clues about this mysterious substance. After all, dark matter could make up around 27% of the cosmos, and yet we still don't know what it is. Like regular matter, dark matter holds mass and takes up space, but it doesn't seem to absorb, reflect, or interact with light, at least not in a way we can detect. Some theorize that dark matter may be made of yet unidentified types of particles. Whatever it is, scientists had high hopes that the overabundance of antimatter being detected aboard the ISS may hold clues about dark matter's true nature. Unfortunately, they've been left disappointed. The more scientists dig into the data, the clearer it's becoming. The most likely source of these positrons may actually be pulsars. Astrophysicists had long suspected this, but until 2017, there simply wasn't proof. It was the High Altitude Water Cherenkov Gamma Ray Observatory that finally added evidence to this hypothesis. A small halo of gamma radiation was identified surrounding Geminga with trillions of times more energy than is visible to our eyes, from 5 to 40 trillion electron volts, the sort of radiation usually produced by positrons. This was the first real observational evidence pointing to a pulsar as a potential source. Pulsars naturally surround themselves with a haze of both electrons and their positron counterparts as a result of the star's intense magnetic field. This intense magnetic field pulls particles from the pulsar's surface and accelerates them to near the speed of light. Scientists think that these accelerated positrons and electrons are then colliding with starlight, boosting the light to higher energies, which then radiates as the gamma ray halo observed. But based on the size of the halo that the Hawk team saw, Geminga's positrons would rarely have the energy required to reach our planet, and so they believed the excess positrons must have a more exotic source. That was until stunning new information was uncovered a few years later thanks to a team led by astrophysicist Matteo Di Mauro. Using a decade of gamma ray data from Geminga acquired from Fermi's Large Area Telescope, which is able to observe lower energy light than the Hawk Gamma Ray Observatory, Di Mauro's team was able to subtract out all other gamma ray sources to reveal a spectacular glow coming from Geminga. Much bigger than what the scientists had ever seen before. The vast, oblong halo of glowing gamma rays at an energy of 10 billion electron volts spanned 20 degrees of the sky, similar to the area the Big Dipper constellation occupies. And that's not all. The glow of gamma radiation is even bigger at lower energies. If we could see it all with the naked eye, Geminga's gamma ray glow would dominate our sky, covering an area 40 times bigger than the full moon. With this new information, astrophysicists found that the size of Geminga's halo meant that this one pulsar alone could be responsible for as much as 20% of the excess positrons detected near Earth. From there, it's no stretch to imagine that other pulsars are the most likely culprit for the remaining antimatter abundance we found. This explanation may not have solved the mystery of dark matter, but it is certainly a magnificent revelation. It was Jocelyn Bell Burnell who discovered the first pulsar in 1967, back when people thought that those regular signals could be the work of extraterrestrial life. In the nearly 60 years that have passed since, we have found thousands of pulsars, and our understanding of these neutron stars has grown with every one. And since Geminga was identified as only the third known gamma ray pulsar in 1991, we've now spotted over 300, thanks to NASA's Fermi mission. But given Geminga's track record of defying expectations and furthering science, I like to think that this particular pulsar has more secrets still to reveal. We've all seen pictures of galaxies, often glorious objects with spectacular colors and shapes. However, because they are static images, it may make you wonder how they rotate. The first obvious thought is that they spin around an axis, perhaps looking something like this as they do so. Would it surprise you to hear that this is totally wrong? For a start, galaxies are not solid objects, but rather made up of millions to trillions of stars. Each star follows their own orbit, although they are often going in the same direction at least. But actually, one of the main reasons a spiral galaxy does not orbit like the first example is that angular momentum would wind the arms up into tighter and tighter spirals. We don't see this, so something else is at play. The leading theory is that these arms are caused by density waves, meaning a galaxy's rotation would in fact look like this. Here the arms stay in place, or at least move extremely slowly as stars and gas pass through them. Another theory is that shock waves produced by supernova and stellar winds are the cause of the arms. These theories might not be mutually exclusive, and both processes may be at work here. Density waves are potentially caused by the self-gravity of stars as they orbit after they have been perturbed by another force. As stars have a gravitational influence on each other, eventually a pattern forms where their orbits meet around certain areas in the galaxy. Very, very interestingly, density waves are even seen in certain parts of Saturn's rings. Here you have a section of ring that appears like the inside of a tree trunk, but this is not the case. In this region, the ring is influenced by the gravity of small Sheppard moons tucked inside the rings. What you are actually looking at is one very tightly wound ring, a bit like an LP record. And just like with a galaxy, this arm stays the same shape, never getting tighter or looser. Within these arms is where the majority of star formation takes place in a spiral galaxy. The gas and dust within a galaxy clump up in these arms too, which is why you often see star-forming nebula dotting the arms. The arms are also brighter, not just because there are more stars here, but also because all the hot, young, bright stars are found in these regions. Because the hottest types of stars are so short-lived, by the time they move away from the arms, a lot of them will have already burned out. Another interesting phenomenon to do with spiral galaxies is something caused by dark matter. In the early universe, when dark matter was more dispersed, stars within galaxies that are dominated by normal matter would orbit a lot slower around the outside of the galaxy than towards the center. However, today, stars are moving a lot faster near the edge of the galaxy thanks to the influence of dark matter. Dark matter is mysterious in that it cannot be seen or observed in any way other than by its gravitational influence. Dark matter seems to have clumped towards the center of galaxies over time, making stars orbit faster than they should around the edge of a galaxy if only gravity from normal matter was accounted for. Other theories also exist about why this may take place, but these would have to change the way we currently understand physics. Anyway, how do we know about this change in the way stars orbit galaxies? Well, of course, we can see back in time when we look at extremely distant objects. Stars within galaxies billions of light years away seem to orbit slower than stars much closer to us, and this effect scales depending on the distance to the galaxy. Of course though, there are some rule breakers out there. While most galaxies have stars that orbit like this, a few have been spotted that have leading outer arms. One example is NGC 4622, a bizarre galaxy that rotates in the direction the arms are pointing. This was hard to accept at first, until smaller inner arms were also found. This unusual galaxy has probably experienced a merger in its not too distant past, which likely caused this phenomenon. Another rule breaker is the Black Eye galaxy, which has two counter-rotating disks of gas and dust. The inner disk, where you can see all the dust lanes, rotates normally, whereas gas in this outer disk rotates the opposite direction. Interestingly, stars in this outer region do not seem to be orbiting retrograde, meaning it is just the gas that does so. It is believed that gas must be still getting fed into the galaxy from the intergalactic medium, or that this galaxy also merged with another extremely gas-rich galaxy. The last thing I wanted to show you today is the other major category of galaxy, elliptical galaxies. Elliptical galaxies contain stars that are generally much older than those found in spiral galaxies because the dust lanes in these galaxies have been exhausted, meaning stellar production has all but stopped. In these kind of galaxies, stars are very much independent from each other, following their own rather elliptical orbits. Sometimes galaxies can exhibit characteristics of both types of galaxies. These are known as lenticular galaxies. These galaxies have dust rings which haven't fully been exhausted yet, and they have quite a ghostly appearance. Star formation does appear to be a factor in keeping spiral arms defined, as once the stellar building blocks dry up, we've seen examples of spiral galaxies losing their definition. Perhaps lenticular galaxies are the midway point between spiral galaxies and elliptical galaxies. So there we have it, a look at how galaxies rotate. When you think about the North Pole, you don't expect it to go anywhere. And you certainly don't expect it to change places with the South Pole. That would just be wrong. our magnetic compasses would all point the wrong way. We'd need to update our maps. Birds would probably be horribly confused. And yet, although they sound like something out of science fiction, geomagnetic reversals like this are real. They've happened before, and the process behind it might be a lot more dangerous than you'd think. To be clear, it's not the reversals themselves that are potentially dangerous, it's the buildup. During those times, the Earth's magnetic field, the shield around our planet that keeps us safe from deadly solar radiation, will drop to as low as 10% of its current strength, leading one group of scientists in 2021 to predict climate shifts and mass extinctions, and others to describe satellites being destroyed, electrical grids going offline, and deadly radiation raining down on us for hundreds or even thousands of years. This is troubling when you consider that we are a couple of 100,000 years overdue for our next geomagnetic reversal, and based on fluctuations in the Earth's magnetic field that scientists are detecting right now, the build-up to a geomagnetic reversal may even have begun already. Which begs the question, should we be worried? I'm Alex McColgan, and you're watching Astrum. Join with me today as we explore the science behind geomagnetic reversals and find out whether the next one will be an apocalyptic scenario or whether it'll lead to nothing more than a few lost birds. What truly happens when things go south? Let's start by trying to understand where the Earth's magnetic field comes from in the first place. It's not a given that our planet would have a magnetic field. The two planets flanking us, Mars and Venus, do not have one, and yet the Earth does, which is a good thing, as without one, there is a very real chance life would not have been able to arise here in the first place. Thanks to the protective cocoon of this field, deadly solar radiation is deflected away from the planet's surface, allowing things to flourish without all that radiation breaking down our DNA, causing mutations and cancers. Scientists are still trying to figure out all the particulars of why certain planets have fields and certain others don't, but the current leading theory is that the Earth's core acts as a giant dynamo. It's a principle of physics that you can use electrical fields to create magnetic ones, and vice versa. This is the principle that power plants work under. Moving a magnet through a coil of wires causes electrical current to start to flow, as that changing magnetic field exerts a force on the electrons present there. But similarly, the motion of electrons creates a magnetic field to form in perpendicular circles around the direction of motion, in accordance with Faraday's law of induction. But the way this applies to the Earth's core is a delicate, complicated process. To start with, our core needs to be at least partially liquid, which fortunately is true. Above the solid inner core that lies at the heart of our planet is a liquid outer core, where the pressure isn't quite high enough to keep things in a solid state. It's very hot in the outer core though, 6,000 degrees Celsius at its warmest point, so hot that it rivals the surface temperature of the sun, which, when combined with the lower pressure compared to the inner core, is more than enough to keep the iron and nickel that makes it up flowing down there. The temperature drops as you move away from the center of the Earth. This gets circulation going. Hot, conductive material from the warmer, deeper regions of the outer core rises, then cools, then falls again, creating loops and currents of flowing material. Our electrical field starts to be generated. But if there are many of these flowing loops, which in theory there would be, why does Earth only have one North Pole and one South Pole? Surely the created magnetic fields would be all over the place. Well, there is thought to be an extra force at play that takes all these fields and unifies them, pointing them in the same direction. This force is thought to be the Coriolis effect. Dynamo theory states that the Coriolis effect causes these flows of iron to not rise and fall as straight lines, but as spirals. The spinning of the Earth causes them to gently be spun in turn, creating giant springs. As each segment of each spring is creating a magnetic field in a circle around it, the net result is that the inside of these springs creates a solid, unified field that all moves in the same direction upwards, while the outside brings that magnetic field looping back down again and back in to the bottom of the coil. In short, it creates the well-known magnetic dipole north and south that we see today. However, if there's anything that you should take away from this, it's that this process is precarious, as it is based on a lot of liquid iron essentially just sloshing around, which is not very consistent. Our magnetic field thus has little fluctuations and wobbles all the time. We see this in different ways, but a big one is that our North Pole is constantly moving. Since scientists began keeping track of it in 1831, the North Pole has gradually shifted about 1,100 kilometers, leaving its original location in Canada and moving up towards Siberia. Its rate of motion is also increasing, going from 16 kilometers a year to roughly 55 kilometers a year, a big jump. This might still be akin to just the momentary wobbles of a spinning top though. Yes, it deviates somewhat, but it always remains roughly upright. That's a far cry from a complete reversal. However, scientists are certain that such reversals have happened before. They even have a specific number, 183 times in the last 83 million years. How do they know? The answer lies locked in our Earth's surface iron. When magma erupts from the Earth's mantle, it can contain small amounts of iron. As these can move freely in the molten magma, they tend to orient themselves in the direction of the Earth's magnetic field. However, scientists noticed that there were layers of geological history where the iron was pointing one way and layers where it was pointing in the reverse direction. Their explanation? The entire pole of the planet had flipped. On average, these flips seem to happen every 450,000 years, although the last few have only got 300,000 year gaps between them. Comparatively, it's been 750,000 years since the last reversal. You might think that we're overdue for one, and some have made that claim. However, scientists have found that there's little rhyme or reason to the timing of these flips. One of the longest gaps between flips took place in the Cretaceous period, and it lasted 40 million years. The record holder, the Kierman reverse superchron, was 312 to 262 million years ago, 50 million years with no reversal. Scientists are still trying to understand what causes these flips. However, the current theory is that something, perhaps some interplay between the mantle and the outer core, causes a fluctuation in the core spinning. This disrupts the spiraling shapes of the core's flow, breaking them down. The magnetic field of the Earth stops being unified and generally becomes a sprawling mess, fighting against itself. Several poles might temporarily arise during this period of shifting magnetic confusion. While in time things settle down and the spirals reassert themselves, it seems random as to which way they will do this, meaning about half the time our magnetic North Pole reappears over the geographical south. This reasserting can take 1,000 to 10,000 years. Alright, but would that really be the end of the world? Why does this matter? Well, during that period before the poles reassert themselves, our Earth's magnetic field drops to as low as 10% of its current strength. In theory, this could leave us much more vulnerable to all the solar radiation space throws at us. We could see auroras reaching much further south during that time. Skin cancer rates would increase. Our satellites would find themselves with not enough shielding. Radiation would fry their circuits, causing them to malfunction, shut down, and potentially even slowly fall from orbit. Our electrical grid would be much more vulnerable to solar storms, which could lead to large segments of the Earth's population without power. With no electricity or satellite communication, it would be a devastating blow to our global civilization. It could be worse than that. A research team from the University of New South Wales in Sydney even linked one of the most recent weakenings of the magnetic field, the Lachamps event, a temporary 800-year wobble rather than a full flip, to megafaunal mass extinctions in Australia, including the deaths of Diprotodon, giant Australian wombats, and Procoptodon goliath, giant kangaroos. Temporary wobbles like this are known as geomagnetic excursions rather than full reversals, and they happen over much shorter timeframes. Their transition periods can last as little as 200 years rather than 10,000, which can be much more difficult for species to adapt to. In their 2021 study, they argued that there was a spike in atmospheric radiocarbon levels caused by the collapse of the Earth's magnetic field, indicating climate shifts that could have led to these extinctions. The timing lines up uncomfortably. But how real are these risks? Honestly, it's a mixed bag. A point in our favor is that other than this recent study, there is no indication that magnetic field reversals have ever coincided with mass extinction events. It seems like many reversals have come and gone without affecting animal or plant life at all. And even in this study, such mass extinctions seem to have been limited in scope. There is no claim from the researchers that this was a global phenomenon. Other parts of the world remained unaffected, even during the Lachamps event. It seems that a perfect storm might have been in play, where specific conditions over Australia left it more vulnerable to solar radiation. In terms of our global society, it's worth noting that these magnetic changes would take many lifetimes to complete, even at their fastest. This would be slow enough that we could come to terms with our new reality. If our satellites don't have enough shielding, we would have time to build some that were better protected. If solar radiation becomes a larger risk, we could remain indoors more. Sun cream might become more powerful to mitigate the dangers of cancers, if not remove them entirely. And according to NASA, even if our field were to significantly weaken, it's not like we would be left without protection. Our atmosphere itself can catch radiation, meaning that we would remain safe from solar winds and cosmic radiation, at least to some degree. It would take far longer than 10,000 years for our atmosphere's ozone to be stripped away. But I would be surprised if there wasn't at least some turmoil, at least while we adjusted to living under a reduced magnetic field. Big changes to how a society operates are always painful. And this isn't entirely hypothetical. Did you know the Earth's magnetic field has been steadily weakening for the last 200 years? It would take another 1,300 years for it to vanish completely, so there's plenty of time for it to stop its current downward trend, and there's no reason to think this isn't just a temporary wobble. But on top of that, there is also the South Atlantic anomaly to consider, a section of the Earth's magnetic field that is already showing signs of significant weakening that covers most of the space around South America and the neighboring ocean. This zone might not influence life on the ground, but is dangerous enough that it has fried satellites and threatened astronauts. The Hubble telescope has to turn itself off every time it flies through it. Imagine that, but across the entire globe. That's what we might expect while the poles are reversing. Concerningly, the South Atlantic anomaly has been growing continuously since we started keeping track of it, possibly suggesting the approach of either another geomagnetic wobble like the Lachamps event, or that a full-blown reversal is already upon us. If it happens, it won't likely be something that ends civilization as we know it. But if the study about Australian megafauna is correct, it isn't going to be without impact either. Species could die. Humans will have to accommodate a very different, more hazardous space environment. It's interesting to learn about geomagnetic reversals and their potential impacts on the planet, but while we are not likely to see one happen in our lifetimes, for the generations of humanity after us, this might turn out to be a lot less hypothetical. They might be seeing it firsthand. Thanks for watching. If you've been enjoying Astrum's videos and want to help keep this channel thriving, I want to ask you to take less than a minute to check out the Astrum Patreon. It's not just ad-free videos, but it's a way to make Astrum's videos less reliant on sponsors and algorithms. The link is below. Your membership directly helps ensure that future videos can stay independent, high quality, and consistent, created for curiosity, not clicks. Thanks so much for considering it. I'll see you next time.